Hello guys! Welcome to Theater. What's up? You a bit confused about the derivatives? Don't worry, because today I'm going to explain to you the concept of derivatives and how to calculate them through the limits and the difference quotient equation. Now, if you don't get it the first time you watch it, don't panic. Don't panic. Just watch it a couple times, and if you're really willing to understand the concept of derivatives, I promise you, you're gonna get it. Let's jump into the video. In the previous video, I explained to you guys how to calculate the slope of a linear function from 2 points. And I also said it was a pretty important video to look at if you're trying to understand derivatives. And this is because the concept of derivatives is based on the difference quotient equation that we use to calculate the slope from 2 points. Now, the concept of derivative is the slope of our tangent line in each point of our function. In a linear function, the slope is constant because it consistently grows the same rate in each point of our function. However, the tangent line changes in each point. Let's just first review the concept of tangent, because maybe I'm just saying this word too much and you don't even know what it means. So a secant line is a line that has 2 points in common with our function, whereas a tangent line is a line that only has 1 point in common with our function. And what we want to calculate is the slope of the tangent line in each point of our function. This is the concept of derivative. The problem is with the difference quotient, we can calculate the slope of a linear function from 2 points, not from 1. And the tangent line only has 1 point in common with our function. So what we're going to do first is calculate the slope of a secant line that has 2 points in common with our function, and one of them is the one that we want to calculate the derivative in. So let's say we want to calculate the slope of the tangent line in this point. First, we're going to calculate the slope of a secant line that has this point in common with our function, but also another one. Let's say that one. And because this is the point that we're interested in, we're going to call this one x. And we're going to call this one x plus h, being h the distance between the 2 points. And the value of our function, so the y value in this point, would be f of x. And in this point, it would be f of x plus h. That makes sense, right? Now, all we're going to do is just substitute in this equation. So, in this case, we called the coordinates of the 2 points x1, y1, and x2, y2. But in this case, we call the x and f of x, and x plus h and f of x plus h. So we're just going to substitute. Let's call point number 1 this one, and point number 2 this one. The coordinates of point number 1, as I said, are x and f of x, x and f of x, and the coordinates of the second point are x plus h and f of x plus h, x plus h and f of x plus h. Now, this and this are going to cancel, and we're left with this. So this would be the slope of a secant line that has 2 points in common, and one of them is the one that we want to calculate the slope of the tangent line in. Now, this is not what we want. As I said, what we want is the slope of the tangent line. But how about we bring this second point so close that the distance between these 2 points is almost zero. How about we make h almost zero? How about we bring this point so close to here that the distance between them is almost zero? What would happen then? What would happen is that this secant line would actually become the tangent line because the distance between these two is so small. Here's where the concept of derivative through limits comes in. The derivative is expressed like this. That's how we call it. So how about we copy the same expression, but when h is almost zero? So this is the concept of derivative. We first calculate the slope of a secant line, and then we bring the 2 points of the secant line so close together that their distance is almost zero, so we can actually calculate the slope of the tangent line. Now that we've understood where the concept of derivative comes from, let's calculate the derivative of the function, just substituting in the equation that we just had. So we have that this is the function that we want to calculate the derivative in, and this would be the value of our function in x, and this would be the value of our function in x plus h. Correct? Because we're just substituting x plus h. So let's just substitute in this equation to actually calculate the derivative. Now, please always use brackets just to make your life easier and try to avoid mistakes. A big mistake that I hope you guys already know about, but just it could be a disaster. This is not this, okay? It's not the same thing. What you do is you multiply each term by each term okay? And this is actually the same, so this would be 2xh. This is the correct answer, so please don't write that down because then all your effort is just going to waste. Now there's a negative sign, so it affects both terms. So it's minus 2x squared minus 1. Okay, now this and this is the same thing, positive and negative, so this and this would cancel. And the same goes for this and this. They would cancel as well, so we're left with that. And if we continue factoring, then we can actually cancel this too, and we're finally left with this expression. Now we keep saying that h is almost zero. H tends to zero. So how about we assume that h is actually zero? If h is actually zero, that would cancel. And we would be left with just this expression, which is our final, which is our solution. So that is the derivative for our function. The derivative of 2x squared plus 1 is 4x. Some of you might be a little bit disappointed or confused because all this time I've been saying that the derivative is the slope of the tangent line in each point of our function. But listen, in each point of our function, like I said, the slope is not constant. It's different that in the linear function case where it was consistently growing at the same rate, like increasing or decreasing at the same rate. In this case, as I said earlier, the slope of the tangent line in each point varies in each point for our function, and that is the reason why our derivative is actually a function as well, because it will give us a different value depending on the value of x, depending on the point that we're actually calculating the slope in. So this might sound a bit crazy, but just hold on because you're going to understand. Imagine if they were to ask us to calculate the derivative when x equals 1. Well, we'll use substitute, and when x equals 1, the slope of the tangent line would be 4. And as I said, the reason why it's a function is because it's going to change depending on the value of x. Because when x is 2, the slope of our tangent line is 8. So as you can see, the value of the slope of the tangent line varies in each point of our function. So this is how you calculate the derivative of a function based on the limits concept. However, this is very long and very tedious. This is not how you calculate derivatives in general. You have like the instant derivatives table that you might use probably always from this point on, unless they ask you to solve this problem through the limits concept. But it's pretty important to actually understand this, just so you can understand what you're doing. If this video made you understand the concept of derivatives and how to calculate them, or it even just made your life a little easier and you feel like you're closer to understand it, I would very, very much appreciate a thumbs up, comment down below, and also share and subscribe.